All right, so last time we talked in particular about the Fourier concentration and nice Fourier properties of decision trees, which are a popular way to represent Boolean functions, especially in learning theory. And today we're going to talk about arguably an even more popular way to represent Boolean functions, and that's with Dnf formulas. OK, so in case you have not heard of Dnf formulas before, this stands for disjunctive normal form, but it's not important. It's just some letters. A DNF is a simple object. It's just an OR of ands. So a DNF formula is the logical OR of groups of variables in the negations. And these groups are called terms. Okay, each of which is the logical AND of some variables. Well, actually, some things called literals, which are variables or their negations. OK, so there we've crammed like 3 definitions into 1 definition. OK, so the picture, if you try to draw such an object as a circuit, is something like this. So you'll have some OR at the top, and it feeds into some ANDs. And then at the bottom of these diagrams, you write the variables, and maybe you can write their negations next to them. Sort of without loss of generality to assume that the only knots, logical knots in these circuits are pushed all the way to the bottom. So here's an example. OK. All right, so this is an example of a DNF. And if I didn't make a mistake, this is sort of the output up here. This computes the function, the Boolean function, which is true. Today I'm going to use true and false for the bits, because when you're talking about logical ands and ors, it's easier than numbers. If and only if the bits are kind of sorted. OK, I think that's right, but you can check if I made a mistake or not. OK. So just to remind you, a Dnf formula is actually a syntactic object which computes a Boolean function in a natural way. But we're going to eventually just identify them in our heads. So sometimes I'll talk about this as a Boolean function, even though it's actually a representation of a Boolean function. And a little bit more terminology, the width of a Dnf formula is the maximum fan-in or arity of the ands. And the size is just the number of ands. OK, in other words, the fan-in of the OR. OK, so I'm using this fan-in stuff is kind of circuit terminology. And probably next class we'll talk about a more general class of representation of Boolean functions, which are constant depth circuits. So if you allow a few more levels of ands and OR gates. OK, so this particular Dnf formula has width 2. Actually, all of the ands here have fan-in exactly 2. And it has size 3, because there's 3 ands. One more piece of terminology. There's an analogous thing if you flip ands and ors, or equivalently if you flip the notion of true and false. What's called the CNF formula, conjunctive normal form. These are the same thing, except it's an and of ors. But as I said, by De Morgan's laws, if you switch the notion of true and false, that converts a CNF to a DNF and vice versa. And from a Fourier point of view, like switching true and false is not really a big deal. It just depends on your convention for what's plus or minus 1. So from a Fourier perspective, DNFs and CNFs kind of have all the same properties. So we're just going to focus on DNFs for concreteness. But whatever I say also applies to CNFs. Any questions so far? People in computer science have probably seen all this stuff a million times, but there's some mathematicians here too. OK, great. So what we're going to talk about today is the fact that functions computed by compact or relatively small Dnf formulas have also pretty simple Fourier spectrums, which is good for learning and in general for studying circuit complexity. This is actually kind of a generalization or a strengthening of what we talked about last time with decision trees. For the following reason, I'll leave this as a little exercise. If f is computable by a size, well, let me say depth k, size s decision tree, then it's also computable by a DNF with similar parameters. Width k, size s, DNF. OK, that's a pretty easy exercise. OK, so basically, whatever you can compute with a decision tree, you can compute at least as efficiently with a DNF, also with a CNF. But the converse is not true. There are things computable by small decision trees or small DNFs that require large decision trees. For example, if you just look at the AND of all the n variables, that's computable by just like an OR of one AND. So that has a DNF of size 1, but a decision tree for AND is going to have at least n leaves. So DNFs are more powerful than decision trees. OK, so as I said, DNFs, and as we'll see also in the next class, constant depth circuits, functions computed by compact such guys, still have relatively simple Fourier spectrum. And these are also like the class of circuits for which, in complexity theory, we have some understanding at all. For example, for which we can prove circuit lower bounds. So DNFs and constant depth circuits are both sort of at the limit or close to the limit of our knowledge for circuit complexity and also in terms of understanding their Fourier spectrum. And these two facts are not completely unrelated. OK. So to prove that DNFs have simple Fourier spectra, relatively simple, we'll start with a very simple proposition. And it says that if f is a width w DNF, OK, and really I should say if f is computable by width w DNF, but I'm identifying DNFs in the functions they compute, then the total influence of f is at most w. Sorry, well, actually that's true, but let me write 2w. OK, and if you want a concrete w to keep in mind, like a reasonable width parameter, as we'll see later, is something like log n. OK, that's a common choice. So this is a pretty good bound on the total influence. All right, now the proof of this lemma or proposition is extremely trivial. So trivial that I can never quite remember exactly how to say the proof. So I'll have to squint a bit at my notes. But to prove this, we'll start with a simple lemma, which is a slightly different way of calculating the influences of a function. So this lemma has nothing to do with DNS. It's true about any function. So let f be some Boolean function. And as I said, I'll write the bits as true and false today. Let I be some coordinate. Then if you look at the probability of a random input x, that f of x does not equal f of x with the ith bit flipped. So far, that looks like the thing you do when you're computing influences. But let me also say equals to true. then that's half of the influence of the ith coordinate on f. Okay, which maybe kind of looks plausible. And in fact, I won't exactly write the proof in words. I'll just draw a picture to convince you that that's true. Okay, so imagine, to prove this little lemma, imagine the Boolean hypercube sitting out there in space. Okay, and f gives like a true or false label to each of the strings. This is the case n equals 3. And we're fixing some coordinate I, so let's say the ith direction. Let's imagine that, I don't know, this is the ith direction. Yeah, I didn't finish the diagram. Yeah, there should be something here and here as well. Okay, so when you're normally considering the influence, if you think about it geometrically, it's the fraction of edges in the ith direction that are, bichromatic, that have one true and one false. Okay, so you kind of go through, you pick a random x, and then by considering x and x with the ith bit flipped, you check the fraction of the time that that's bichromatic. So actually, in that little experiment for influence, this edge, for example, this is a bichromatic edge. It goes between true and false. It kind of gets counted twice, right? Once when you pick this to be x, and once when you pick this to be x. Okay, whereas in this experiment, it's the exact same thing, only you only count each edge once, right? Because you only count it for the time that f of x equals true. All right, so you would only count it once when you choose this to be x. Okay, but every bichromatic edge has one true label and one false label, so you get this factor of a half. Is that proof by picture okay? Okay, good. So I needed that little lemma. And I only used that lemma because, well, it's like an equivalent way to compute influences if you're willing to multiply by 2 at the end. And this is actually easy to bound for DNF. So let me now prove the proposition. Okay, so we want the total influence of f. That's the sum of all the influences. Okay, so up to a factor of half. No, wait. 2, right? So it's 2 times the sum over all I of the expected value over x of the indicator that true equals f of x equals f of x with the ith bit flipped. It's just the same as writing the probability. Did I do something wrong here? Yeah, thank you. Okay, and now I'll interchange these things. So I get 2 times the expectation over x of the sum of this over I. So that's equal to the number of coordinates I such that true equals f of x does not equal f of x with the ith bit flipped. Okay. So now let's just try to analyze this. So imagine you pick a random x, and now you're trying to count the coordinates for which this happens. Well, this is 0 if f of x is not equal to true, because then this never happens. So it suffices to bound this in the case that it is true. So suppose then that x makes f true. Okay, I erased my picture of a DNF, unfortunately. It has an or, has a bunch of ands. And each and has fan in at most w. So if x makes the function true, then there has to be at least one and which is made true. At least one term A true. And now I claim, let's say it makes this one true, then any coordinate which does not appear in the fan in here cannot be pivotal. Because for any coordinate that's not touched by this and, if you flip it, it's not going to affect the fact that this and is true. And as long as this and stays true, the whole function is true. So any coordinate not in A is not pivotal on X. And, well, by assumption, the thing has width at most W. So therefore, there are at most W pivotal coordinates for X. OK, so for any X, this quantity is either 0 or it's at most W. So we conclude that this is at most 2W. Any questions about that? Yeah, we need to use this little lemma because if you try to do the analysis for like how many coordinates could be pivotal when f of x is false, you can't actually bound it in terms of the width. OK. Yeah, as I said before, actually, I wrote this by mistake. It's actually true that you can put less than or equal to W here. The first time I taught this class 5 years ago, I made that like an open problem on the homework, and nobody solved it. But then it was later solved by a person called Amano about a year ago. And the proof is pretty simple, actually. Also, this bound of W is sharp. You cannot improve W. Can somebody tell me why? It doesn't necessarily mean that the total influence is equal to W. I mean, to show that it's sharp, you need to give a Boolean function computed by a width W Dnf whose total influence equals W. Yeah?
Just a single and? Or?
Nope. A single and of width W has total influence, well, very small. And has total influence like less than 1.
Any more exact way to represent an XOR except with lots of things?
Yeah, you're on the right track. The XOR function, the parity of everything, is a function that has very high total influence. And let me ask you this. If you want to compute the...
And so if you wanted to do that and have depend on W bits, then each and would have taken at most those W bits.
Exactly right. So the function could be the XOR, or parity of the first W bits. That has total influence exactly W. And since the function only depends on W coordinates, you can, well, actually, this is not totally clear, but every function is representable by some DNF. And in particular, if only W coordinates are relevant, then all the ands only need to have fan in W. OK, so this is sharp, but 2W is close enough for us. OK, great. So, well, I was going to bring this back to spectral concentration. So, as we saw last time, if you remember that far back, there's a connection between total influence and spectral concentration. As a corollary, we get any width W Dnf F is epsilon concentrated. Its spectrum is epsilon concentrated up to degree. Can somebody tell me what I can write here? I.e., does somebody remember what happened on Wednesday? Yeah, it's the total influence over epsilon. So we can put 2W, or actually W if we want, epsilon. Remember, this means that the sum over S bigger than this bound, 2W over epsilon, F hat S squared, is at most epsilon. OK, and the reason that's true is, suppose this were false, remember, the total influence has this formula, sum over S, cardinality of S, f hat S squared. So if you had weight at least epsilon on sets of cardinality bigger than 2W epsilon, then when you plugged it into this formula, this thing would exceed 2W, in contrast to the fact that it's at most 2W. OK, so yeah. Actually, as we'll see next time, you can improve this fact. You can actually this is improvable to O of W times log 1 over epsilon. OK, so that's better exponentially in epsilon. But for today's class, we're going to be talking about like two parameters like this, epsilon and W. And we're not going to stress out too much about epsilon. So think of it as like 1% in your head. So in particular, this is degree O of W, I don't know, let's say for epsilon equals 0.01. OK, so if you have a width W Dnf, you can get 99% of its Fourier weight by going up to degree O of W. OK, and we also saw that these low-degree spectral concentration results were nice to have for a big class of functions, because then you can use this generic low-degree learning algorithm, which, given random examples from a function, just estimates all of the low-degree Fourier coefficients and basically outputs its approximation to the Fourier expansion, maybe with a sign at the front. And that gives a good learning algorithm. So as yet a further corollary, with W DNFs are learnable even in this weak random examples model. Let's say it's an error, I don't know, 0.01 in time. What? How much time will this take? Yeah, exactly. N to the W over epsilon, n to this bound. Yeah. Yeah. So we can fix all these epsilons to 0.01, and this will be polynomial in n to the W. OK. So that's a medium good for a learning result. I'll come back to how good that is in a second. But if you think of the popular setting I mentioned, maybe W is like log n. This is quasi-polynomial time. OK. Now, it's actually in learning theory and in the study of circuit complexity as well, it's somewhat more common to focus on the size of a DNF rather than its width. Somehow, for like proving stuff, like the width is the best parameter. But if you just think about it naturally, people care more about size. But these are related quantities. So I'll leave the following statement also as an exercise. If f is computable by a size S DNF, then for all epsilon, it's close to a function which is computed by a narrow DNF. Exists G computable by a width log S over epsilon DNF such that F and G disagree on at most an epsilon fraction of coordinates, or epsilon fraction of inputs. OK, and the proof of this is very similar to the analogous statement for decision trees, which I mentioned a couple times. If I give you, a DNF with some S terms, perhaps some of them are freakishly long, like the ands involve like a ton of variables. But those ands are kind of irrelevant, right? Because at least under the uniform distribution, a huge and is unlikely to be anything but false. So if you just truncate all of the terms in the DNF to this width, or I should say just delete all of those terms, the probability that like a term bigger than this will affect the outcome is like epsilon over s. And so you can union bound over s terms. OK, so we know that if you have a size s DNF, you're close to some width-bounded DNF. This, by the way, is equal to the probability over x that f of x does not equal g of x, which is equal to a quarter the expectation over x of f of x minus g of x squared, at least in plus or minus 1 notation, right? Because if they're unequal, you count 4 here, and if they're equal, you count 0. And this is a quarter f minus g 2 norm squared, which is a quarter sum over s f hat s minus g hat s squared by Parseval. Okay, I didn't exactly make this clear earlier, but if you have f and g that are close, it implies that their Fourier coefficients are kind of close in 2 norm squared. And as a conclusion, since we know G has good spectral concentration, we can conclude from this that F also has good spectral concentration. So it's a corollary. If F is a size S DNF, its spectrum is epsilon concentrated up to degree. Let me just write O of log S over epsilon. Any question about that? So in learning theory and circuit complexity, it's most common to think about poly-size DNFs. That's the most interesting class. So a very common parameter setting is S equals polynomial in N. OK, so this means this class of functions, functions computed by poly-size DNFs, are concentrated up to degree log n. And that's why I was saying before that the W equals O of log n is kind of the analogous setting there.
For the corollary, you're using the two left words together?
Which corollary?
So for the
This one?
yeah. So
Yeah, we're using
approximating by small width and then use the other corollary.
right.
But would that give you log S over epsilon, or because the width is that, but then you need degree of this over epsilon, right?
Oh, yes. Excellent point.
Or maybe you use the other.
No. You're right.
Just add a log.
Like that. Right? Thank you. Yeah, that's a good point. Somehow in my head or in my notes, I got too carried away with this idea of like, let's just fix epsilon to be 0.01 in my head. Yeah. So actually, this is, by the same reason of this is actually improvable to log 1 over epsilon, as we'll eventually see. Yeah, but if there's too many parameters floating around, do like I do and just imagine epsilon as a small constant.
Wait, so independent of that?
No, sorry. Yeah. Using this improvement, you can make this log S over epsilon times log 1 over epsilon. OK. Any more questions? OK. All right, so for a similar reason in turn, polysize Dnf are learnable from random examples, error 0.01 in time n to the O of log n. And this is actually the best running time known for this class. It would be great to do this in polynomial time, but it seems hard. I think it's actually not possible. But you can do it in quasi-polynomial time, which is kind of OK. So it would be great, actually, to get polynomial time algorithms for these problems, to do a little digression into learning theory. But it doesn't, as I said, I think it's not really, I would conjecture that it's not possible if you only have random example access. Now, as we saw last time with the Goldreich-Levin algorithm, if you have query access, instead of getting random examples, you can ask for examples on any string you want. That's more powerful, and you can do things like find all of the large Fourier coefficients of the unknown function, as opposed to just hope that they're at low degree. And as we saw, that in particular means that if you knew that function, a given function had most of its Fourier mass concentrated on a small collection, let's say a poly-size collection, then you would be able to learn it efficiently in the query access model. So that actually motivates a well-known conjecture in analysis of Boolean functions, which I'd like to mention, called Mansour's conjecture. Made by Yishai Mansour in 1994. And he made something a little bit stronger than this, so I'll put a little star. But the weaker form of the conjecture, which is still open, is just fix epsilon to be 0.01, or any positive constant. You can conjecture that the width W DNFs are epsilon concentrated on a collection of just exponential in W many coefficients. Okay, and if you care more about size, the conjecture is that a size S DNF are epsilon concentrated on a collection of poly S coefficients. Okay, so actually, as I said, Mansour conjectured something more strong. He actually said what the dependence on epsilon should be, but never mind about that. Also, he only made his conjecture for size S DNFs. This width variation is natural, but it wasn't actually raised until a paper from this year by Mecca Gopalan and Reingold. Okay, and this, if true, would be great. You'd say, oh, this means that, let's say, poly-size DNFs have almost all their Fourier spectrum on polynomially many Fourier coefficients, so we could learn them in polynomial time using Goldreich-Levin, say, with query access to the function. Now, as that happens, that's actually already known how to do that. So Jeff Jackson, who was a PhD student here at CMU, showed that you can learn DNFs given query access in polynomial and S time. So it's actually a learning problem that we already know how to solve. But this is still relevant for learning theory. For example, if you had this, it's known that you could also learn poly-size DNFs in this harder agnostic model of learning. So I won't get into any more learning details, but this is still very relevant for learning theory, trying to prove something like this. And it's just a very natural-looking statement about a basic class of Boolean functions. So that's kind of a dream goal that's been open for some long time, 18 years. And Mansour himself actually improved on, well, he came somewhat close to proving this. So 1 year later, he proved the following, and we're going to prove this next class. He actually showed that width W DNFs are 0.01 or epsilon concentrated on, at most, well, it's somewhere between n to the w, and which is what we know from the total influence bound, and 2 to the w, which is what we're dreaming of. What could that be? Somebody want to guess? Something smaller than n to the w, but bigger than 2 to the w? Yeah, w to the w. W to the w. And for size, sort of equivalently, or actually that implies for size SDNFs, this actually implies for size DNFs, you can get at most, basically you get to replace w by log s. So that's O of log s to the O of log s. Okay, which is, you bring this log down and this one goes up becoming a log. That's like s to the O of log log s. And as I said, this is like tantalizingly close. Like if you take s to be polynomial size, s is poly n, then this is like n to the log log n. You want like polynomial in n ideally. So it's very offensive to like have a theorem that gets you all the way down to n to the log log n, but not down to polynomial. Okay, so that would be a great open problem to try and resolve.
Is there a reason it can't be log 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 s?
No, I mean, hopefully we think it's actually polynomial in S. So we'll see next time how to prove this, and if you see how to get another log in there, that would be outstanding. Okay. Any questions about this? We're going to like actually start proving some things now. Okay. Yeah, so the technique we have to start talking about some Fourier analysis eventually, and the technique that we're going to use is related to the technique of restrictions that we talked about last time. And in particular, we're going to look at random restrictions. So before we get to that, let me make a little observation. Here's a theorem that we're going to prove soon. Let f be computable by a size s Dnf formula. How can we bound the total influence of f? What can we put here? So remember, if it was with w, we could put like 2w here. So what would you guess that we could put here? Yeah, you would guess that we could put log s. And indeed, that's true. Unfortunately, it does not quite follow from what we've proved so far. I mean, in my head, I would think, OK, we kind of know that f is epsilon close to log s over epsilon with Dnf. And this has total influence at most 2 log s over epsilon. But just because you're close to a function with low influence, it does not mean you yourself have low influence. Well, you think about why. For example, if you take any function, Boolean function with low influence, and you just randomly change its values on an epsilon fraction of inputs, then this corrupted function will be epsilon close to the guy with low influence. But actually, if you think about it, its total influence will be like linear in n. It could be huge. So this suggests, these observations suggest that this might be true, but we haven't actually proved it. So that's one thing we'll end on today, proving this theorem. And as I said, we're going to do it by the method of random restrictions. Actually, two guys, Liang Tan and Eric Blais, I think they have like a new proof of this that uses the entropy method and doesn't use Fourier analysis or anything. So I look forward to seeing that. But for now, we'll do an old-fashioned Fourier-based proof. OK, so let's switch gears a little bit from concrete complexity and instead talk about random restrictions in the connection to Fourier expansions. Okay, so let's make it into a definition. So random restriction is like the restrictions we talked about before. In addition to like making the fixed bits random, we're also going to choose the coordinates that we don't fix, the domain of the restricted function, to be random. Okay, so let me make a definition for that. For some parameter delta between 0 and 1, a delta random restriction means the following. Okay, you imagine you have some Boolean function, and you're going to restrict some of the coordinates. So for each coordinate I independently, with probability delta, leave it free. Okay, don't restrict it. And with probability 1 minus delta, fix it to plus or minus 1 with equal probability. Okay, so let me kind of do a little example over here. Imagine you had a function like majority on 5 coordinates. So there's like 5 coordinates, 1, 2, 3, 4, 5. Okay, you just go through the coordinates one by one, and like you either decide to like leave it alone, leave it free. So I'll denote that in this picture by writing a star. Or maybe you set it to plus or minus 1. With probability 1 minus delta, you like flip a coin for its value. So then maybe you leave this free, this free, and maybe you make that minus 1. Okay, and then for this particular case, you get a restricted function on 3 bits. Actually, it would more precisely be the majority of the first, third, and fourth bits. Okay, another way to look at this is to do it as follows. First, you let J, this means J is a delta random subset. Okay, so you go through each coordinate and you include it into the set J with probability delta. And then you choose, this will be like the domain of the new function, and then you choose bits uniformly at random from the complement of J, which we were denoting by J bar. Okay, and then together, this pair, J and Z, is our delta random restriction. Okay, and given a Boolean function f on n coordinates, from last time we wrote the restricted version of f sub j z. Okay, so this is the bits that are still free, the coordinates that are still free. These are the ones that we fixed randomly. But now in this world, the coordinates j are also chosen to be a delta random set. I'm saying this purple stuff is equivalent to this black stuff. Okay, one more thing notationally before we do a little math. You see, this is our restricted function, f sub j bar z. And here's an example. And the new domain of this function is kind of minus 1 to the set 1, 3, 4, which is very annoying because it's annoying when like the domain of the restricted function is like a random variable. It causes like tremendous notational heartache. So what we're going to do in the case of random restrictions is we're going to identify always the restricted function fjz, which technically maps minus 1, 1 to the j bar into the reals, with its extension to the original domain. It just means you ignore the J bar inputs. Okay, so what that would really mean in this case is we'd still think of this restricted function, majority sub 5 on this restriction, as having domain -1, 1 to the 5. It's just the first thing you do when you see a string is ignore what's in 2 and 5. And you only care about the coordinates in domain in the set J. You have a question about that?
Just to clear that, should that be -1, 1 to the J?
Oh, yeah. Thank you. Yeah. Good. Yeah. Yeah, it's important to correct these little mistakes because there's so much notation happening that you're like, is it a function of J, J bar? It's J. Okay. So the good thing about random restrictions is that they have some beautiful properties both for the combinatorial side of things, like, I don't know, what happens when you apply random restrictions to DNFs or decision trees. And they also work out very nicely with the Fourier side of things. As we'll see in a second, you can understand the Fourier expansion of the random restriction of a function in terms of the original Fourier expansion very nicely. And so this combination of two things, looking at functions under random restrictions from the combinatorial side or the concrete complexity side, and also from the Fourier side, is very powerful. Okay, so let's do the main two facts about how the Fourier expansion of the random restriction of a function looks. And this will be similar to the theorem we saw last time, which is hard to remember, but you should at least know that these formulas existed, to the formulas for the Fourier expansion of a fixed random restriction to f. Okay, so let's let f be a function into the reals. And let's let jz be a delta random restriction. Okay, so that'll give you a function that really only depends on the j coordinates, but by this convention, we'll think of it as a function on all n input coordinates. So we can ask about its Fourier spectrum. So let's also let S be some subset of coordinates. Okay, so here are the two formulas. So the first thing we'll be interested in is just what's the expected value of the restricted function's S Fourier coefficient. So this is the expected value of f with the restriction of S. Okay, this is over the random restriction. All right, and that will have this nice formula. It's delta to the cardinality of S times the original Fourier coefficient. And 2, we're also going to need to know the same thing, but for the square. Okay, and that's slightly more complicated. It's the sum over all subsets u of n of the probability that u intersect j equals s times f hat u squared, which is equal to the sum over all u's. Okay, here we have the probability. U is a fixed set. S is a fixed set. And you're asking, when I choose a set j at random, what's the probability that u intersect j will equal s? So there are two cases for analyzing what this quantity is. Can somebody suggest what those two cases are? Well, let me start by saying this. If u does not already contain the set S, then this probability will be 0. So we should actually just sum over the u's that contain S. Okay? And if u does contain S, then for every guy, not quite. Remember, J is a delta random set. Each coordinate is included with probability delta. Yeah, so for each coordinate in S, you need to include it into J. That's this much probability. And for each coordinate that's not in S but is in U, you need to not include it. Okay. All right, so again, I'm not going to insist that you memorize these formulas, but you should know that there are some pretty nice formulas which you can look up or rederive when you eventually need them. But now we will prove them. Okay, and the proof is, I mean, it's very straightforward in the sense that what we're going to do for both things is just first imagine that J is fixed. Okay. Then what we have is J is some fixed set, and we're just choosing the Z coordinates, the stuff outside J, randomly. And when you do that, we had the formulas for the expected value of the restricted function's Fourier coefficient and its square. You might not remember them, but I'll write them down. So we have the formula for when J is fixed, and then we just take the expectation of that formula over the choice of J. Okay? So here Z is still going to be random in J bar. But remember, we're going to think of this guy as still having domain minus 1, 1 to the n. OK, so if you recall from last time, let's start with just this quantity. The expected value over just the choice of Z of f j bar z hat. Does anybody remember what this is? No? Yeah, it's f hat s. Now, it's f hat, you know, it's just the original Fourier coefficient. Now, it's f hat s. Well, I mean, last time we were only considering it when S was a subset of J. Like, it's f hat s when it's a subset of J. Because this guy really only depends on the coordinates in J. But for completeness, I mean, now we're thinking of the domain as being everything. So if S is not a subset of J, it'll be 0. I mean, if you think of the Fourier expansion, if you add some like irrelevant coordinates, it doesn't really change the Fourier expansion at all. So the full statement, if we think about this as the domain, is it's just f hat s, you know, assuming that S is a subset of J. Okay, and if S is not a subset of J, then it's just going to be 0 for every Z, in fact. Okay with that? Okay, so now then 1 is done. So now 1 follows by taking the expectation over the choice J. Okay, because this just gets converted, the expectation of this indicator gets converted into the probability that J will entirely include the set S. And that just means for each coordinate in S, you better pick it. So that has probability delta to the cardinality of S. Okay, and part 2 will be very similar. If you actually took notes, now would be like a great time to like scurry back to like last class's notes, look up for the formula for the square. So then if I ask anybody if they remember what it was, they can say, yes, I do. I can tell it to you right now. Okay, so yes, in this case, when J is fixed and Z is random, we recall that the expected value over Z of the restricted function hat S squared is equal to, does anybody remember?
Yes,
Misha?
you right now.
Oh, great. Yeah.
It's the sum over all the T contained in J bar of f hat of S union T squared.
Yeah, that's right. Great. OK, so now that I have you here, that's correct, as we know, assuming that, again, S is contained in J. Okay, so how can we write this? See, this is not that's correct, but it's still not the best, most enjoyable way to write it because the sum still kind of depends in the index on the future random variable j, which is a little annoying. So how can I write this as the sum over all u of f hat u squared times something? What would this indicator be? I mean, basically I'm asking when is u such that it's of the form S union T equals u for S in J and T in J bar. Okay, I think by saying those words, it like made it more confusing than it was.
Don't you count some twice?
It depends what I'm going to write here, I guess. It's the indicator that u intersect J equals S. Okay. This is exactly that. I mean, I'm saying these two things are the same thing. Because basically you want that like the Fourier coefficients where the J part is S and the J bar part is whatever. Okay, so if you reflect, you'll see that it's that. Okay, and once you reflect and see that, then 2 again follows by taking the expectation over J. Okay, this will just turn into probability over J that u intersect J equals S. Okay, how about a question about that? It's okay? Just want to go on? Okay. As I said, it's a simple calculation. You just have to do it. But it's best just to remember that there are relatively pleasant formulas for these two quantities. And we're going to use that in this class and the next one. Okay, so as a minor illustration of how nice it is to have these formulas, let's do a computation to get the expected total influence of the random restriction of a function. Okay, so this is a corollary. In this same scenario where f is a Boolean function and jz is a delta random restriction, we may look at this restricted function and ask about its total influence. Well, this is a random variable. It depends on the restriction. So let's ask about what its value is in expectation over the random restriction. And very nicely, it's equal to just delta times the total influence of the original function. Okay, so maybe it's slightly plausible. I mean, when you do a delta random restriction, originally there are n coordinates. In expectation, the number of like free living coordinates after you do that will be about delta n. So somehow things reduce by a factor of delta. And in the case of total influence, it's exactly like that.
Can we prove that with the first proposition and using the size and Fourier coefficient formula for instance?
Yeah, exactly. We'll use this one. You need this square. Yeah, that's what we'll do. Actually, you don't need to use like kind of Fourier analysis to do this computation. As you'll see on the new homework, which is out today, there's just like a simple direct probabilistic argument that shows this, which you're asked to find. But since we have these Fourier formulas handy, we'll do it this way as well. Okay, so just as Arda suggested, this expectation of the total influence of the restricted function, we can get at it just by using the Fourier formula for total influence. So this is the expectation over the random restriction of the sum over all Fourier coefficients, the cardinality of S times the S Fourier coefficient squared. Okay, and normally we would just sum over the Fourier coefficients that are like the domain of F. S is a subset of J, but it's okay that we sum over all of them because the ones that are not a subset of J are just 0. Okay. So now we should, as always, just switch the expectation and the summation. So we'll get summation over S. We can bring the cardinality of S out. Expectation over J and Z of F, J restricted to Z, hat S squared. Okay, now we'll use this formula. In fact, we'll use the first line. So yeah, this is sum over S of the cardinality of S of this thing F hat S squared times the probability that, wait a minute. Yeah, have I done something funny here? Yeah, I need a sum here. Yeah. Good. I should copy what's written there. Sum over U. The probability that U intersect J equals S. F hat U squared. Okay, so now I can interchange these guys. Get the sum over U, F hat U squared, times, this is going a little different from how I had it in my notes. Let's hope it still works. Sum over S, cardinality of S, probability that U intersect J equals S. Okay so far? I see. And what's a simpler way to write this? Yeah, expected size over J of the cardinality of U intersect J. Okay, so what is the expected cardinality of U intersect J? Yeah, so there are cardinality of U elements, and each of them is in there with probability delta. So it's by linearity of expectation, delta times cardinality of U. So overall, we've got delta times the sum over U of F hat U squared, cardinality of U, which is delta times the total influence of F. Okay, any questions about that? All right, so as I said, this was kind of more for practice. There's a more direct way to see this, but in the next class, we're going to do some more powerful calculations of this type, so it's a good warm-up. All right, so actually, I can talk about that a little bit more. So one thing that we'll see, or the main tool we'll use in the next class, is a very powerful result in concrete complexity called the switching lemma, proved by the most powerful form is proved by Hostad. And the Hostad switching lemma says that if you take any Dnf formula, which is got width W, and you do a delta random restriction to it, then roughly speaking, with high probability, it gets really killed. So like with high probability, it becomes extremely simple, like a constant depth decision tree. And that's a very powerful statement about what happens to DNF under a random restriction. And when we combine that with our understanding of what happens to the Fourier spectrum under a random restriction, we'll get to be able to say good things about the spectral simplicity of DNF. So to end this class, we'll do like a very simple result that illustrates this connection between what happens on the combinatorial side and what happens on the Fourier side. But it won't use the Hostad switching lemma. It'll be very simple. But it's also a good warm-up for next class. OK, so the last thing we'll prove is this theorem that if you have a size S DNF, its total influence is at most O of log S. Okay, and for that, we'll just need a very simple lemma about what happens to DNFs under random restriction. In fact, this lemma will just be about what happens to terms under random restriction. So let A be a term in a DNF. So that's some and of literals. And fix any natural number W. And let's say we do a half random restriction. Okay, so about half the coordinates get set, and about half the coordinates remain free. Then the probability that A, when you apply this random restriction, actually the notation I'm going to use here is not so great, but you'll understand what I mean, is width greater than or equal to W is very small. It's at most 3/4 to the W. Okay, so what I mean here is, if you imagine like an and of literals and you're doing a random restriction, a couple of things that could happen. Maybe you'll set some of the variables or literals to be true, in which case it'll sort of just shrink the size of the term, the and. Or you might set one of the literals to be false, and that will just totally kill it. Okay, and it's like width 0 kind of in that case. And so what we're saying in this little lemma is that for any W, the probability that you still need width W is exponentially small in W. Okay, and the point here is that it has no dependence on n. Okay, it doesn't matter if the original term was tiny or huge. We still have this bound. Okay, so the proof of this is quite simple. We can assume, without loss of generality, that originally A has width at least W. Because if A, the original term, already had width W or smaller, then it's only going to get smaller when you do a random restriction to all the variables. Okay, we'll come back to that later. So now, under the random restriction JZ, for each literal in A, the probability it gets fixed to false is exactly what? 1/4. Yeah, because for each coordinate, the probability that it gets fixed is a half, 1 minus this number. And then condition on that, it's 50-50 that it'll be true or false. That's true of the literal and the variable. So probably it gets fixed to false is 1/4. So great. So the probability that it well, as you see, unless the first W literals in it all don't get fixed to false, wait a minute, what am I trying to say here? Yeah, it'll have width 0. Okay, here's where we use the fact that it has at least W literals in it. And the probability of this is 3/4 to the W. Okay? All right, great. So that's a nice fact about terms. Okay, and now we'll end by proving this theorem. F is a size S Dnf, its total influence is at most O of log S. Okay, and we're going to use random restrictions. So let JZ be a 1/2 random restriction. And let's look at the Dnf width of the restricted function. Okay, the least width you need to compute the restricted Dnf. That's a random variable. It depends on the random restriction. So let's call it capital W. And we know by this previous corollary that, or this previous lemma, that the probability that W is bigger than some fixed little w is at most S times 3/4 to the little w by the lemma and a union bound. Okay, just by union bounding over all the terms, of which they're at most S, all of them get to width smaller than w, except with this probability. Okay, so it's very likely that this guy will become a small width Dnf when we do a random restriction. And we know that small width Dnfs have small total influence. Okay, so the total influence. Okay, one thing we know is that the expected value of the total influence of the restricted function is equal to delta times the total influence of the original function, which in this case is 1/2. So by losing this factor of 2, it suffices to show that the expected value of the total influence is at most log S. And we also know that this is at most the expected value of 2 times the expected value of the Dnf width of the restriction. Okay, because one of the first things we did in this class was to show that if you have the Dnf of width w, its total influence is at most 2w. Okay, so this is 2 expected value of w. Okay, so the last thing we need to check is that the expected value of capital W is at most log S. And that's a very simple calculation just based on the fact that we know W is sort of exponentially likely to be a large value. Okay, so just to complete this calculation, the expected value of W, there's this simple formula for the expectation of any random variable. It's the sum over W from 1 to infinity of the probability, that's a little w, W exceeds little w. Okay, so for the first, 10 log S terms, is that a good choice? We'll just say this probability is at most 1. And we'll take the remaining terms. Okay, and now we'll use this bound. So it's 10 log S plus the sum over W bigger than 10 log S of S times 3/4 to the little w. Okay, and this is like a geometric series, so we get 10 log S plus the first term, which is S times 3/4 to 10 log S times like 1 over 1 minus the ratio, which is 1 over 1 minus 3/4. That's just 4. Okay, so we get O of log S. And then this thing is like S times, 3/4 to the 10th is like some very small number. So like, I don't know, 0.1 perhaps to the log S. Okay, and this is like smaller than 1 over S. This is much smaller than 1 even. Okay, so the whole thing is O of log S. Any questions about this calculation? Okay, so next time we'll prove, this is like a very, these two facts are kind of baby facts about what happens when you do a random restriction to a DNF. Next time I'll tell you about Hostad's switching lemma, which is a very powerful fact about that.